Precalculus, lesson 15.3. So this lesson is called Area Under a Curve. I think a better name for it might be the formal definition of an integral, especially because lesson 2, 15.2, was called derivatives, or something along that line. Derivatives and antiderivatives. So a derivative, again, is a formula for finding the slope of a tangent to a graph. So if your function is function f, we have f of x, the derivative of that f prime of x is a formula for finding what the slope of your function is at some particular x value. The integral is a method for finding the area under a curve. And so with with lesson 2, we had within the one lesson the lengthier formal way, definition way of finding a derivative. And then we had kind of a quick, here's how to quickly find a derivative if you're dealing with polynomials. Lesson 3 in its entirety is just the lengthier formal way of finding an integral. And then lesson 4, we will get the quicker, more straightforward way of evaluating an integral with the polynomial again. So this lesson kind of lays the groundwork and gives us the idea of what's going on. So here we go. This is 15.3. And the textbook calls it area under a curve. Area under a curve. I think it also could be called formal definition of an integral. So when we say area under a curve, here's what we mean by that. Axes, okay, x-axis, y-axis. Now, if we had like some line, and we wanted to find what the area between the line and the x-axis was, let's just say not even necessarily starting at 0, let's just say we wanted to find this area. Well, geometry will serve us just fine because we have some form of a four-sided polygon, right? And you could find like the area of this rectangle and then find the area of this triangle and add those two and you're good to go. But what if we add curves? So what if we have something like this? And we want to find something like this area here. Well, geometry geometry and algebra are not going to do the trick for us because of the curviness that is going on up at the top here. So the area under a curve, we're finding from the curve, from the function, from the graph, down to the x-axis, from some starting x value to some ending x value. And we'll define the area, the integral, as being dx, meaning a delta x, meaning we're going from some x value to some y value. You can evaluate integrals dy, so this would be dx. You can evaluate integrals dy, which if you did the same thing, let's just say we do roughly the same curve like this, but let me change the shape of it to make it a little more apparent what we're dealing with. We'll say we have this. Dy would be starting at some y value, going to some other y value, and evaluating the integral kind of to the side of the curve instead of under the curve. So this would be dy, but we're dealing dx. Okay? So here's the idea. Here's the idea. Let's say we do some drawing again. And we have some curve going on again. And let's say we want to evaluate from there to there. So we're going to call our starting value, our starting x value here, A, and we're going to call our ending x value here, B. Now, what if we took this and we split it in half? So we go exactly halfway between A and B, and we form two rectangles where this value and this value serves as the height of our rectangles. And so we draw a rectangle like that, and then we have a rectangle like that. Okay? And what we'll say is there's some width here that we have that is delta x, and because we cut this in half, that's also delta x. And what we will say is this is our first x value that we're plugging into our function. And so if this curve is f of x, then the height here, this point, the x value would be x sub 1. The y value would be f of x sub 1. And then this point here, the x value would be, well, another way, I'll save that for later. This would be x sub 2, which is b. We'll say x sub 2, comma. And what's the height is going to be f of x sub 2. So then how do you find the area of a rectangle? Well, area of a rectangle is width times height. Well, what's the width of this rectangle? It's delta x. I'll go ahead and say width times height, like w times h. W times h. Oops, that's not an h. W times h. What's the width? Delta x. What's the height? F of x sub 1. Same thing. What's the width of this rectangle? Delta x. We'll say area. Again, width times height. Width is delta x. The height is f of x sub 2. Now, have we kind of approximated the area under the curve? Yes. Are we a bit off? Yes. And our first rectangle is overshooting the area a bit. Our second rectangle is undershooting the area by quite a bit. So in this case, we're going to end up with an area that is too small. So what if we took this same idea, but we just split it into more rectangles? I'm going to take the same setup. I'll try to get something approximately the same. I think I might be able to copy and paste here. Let me see. Yeah, perfect. So let's bring this down. A little bit more. Yep, somewhere around there. Okay. And we're going from here. Where am I clicking? Oh. Okay. And we're going from approximately, here's our A, and here's our B. So what if instead of just the two rectangles, we split it into 4? So now we have this rectangle. Pretend that's a rectangle, top of a rectangle. And we have this rectangle. These are all supposed to be the same width. I know I'm a bit off. And this rectangle. And this rectangle. Okay, well, this is going to be better because that huge gap up there is now largely filled in. So this is going to be closer. We're a little bit too high. We're a little bit too high. We're a bit too low. We're a bit too low, but it's going to be better. So the idea of an integral is to continue doing this, but we split this area into a number of rectangles where if n is the number of rectangles, we're going to split this into rectangles where n approaches infinity. Thus, we will find the area of an essentially infinite number of rectangles, where the width of each rectangle is infinitely small. So that's the idea. So we could also define this x value here. So we have a delta x, right? And another delta x, and another delta x, and another delta x. And we could say that our first x value here, x sub 1, is a plus delta x. So take our initial value, add 1 delta x. This x sub 2, we could say is a plus 2 delta x. Because we started a, we added delta x, we added delta x a second time. So this x sub 3, we could say is a plus 3 delta x. So notice the subscript of what x value we have matches how many times we are adding delta x. So then our final one, b, is x sub n. In this case, it's going to be 4, but I'm making it generic, which that is a plus n delta x's. And then likewise, the height here, we could say is f of x sub, actually I don't want to go with an n there because we're split. Here's what we have. N equals number of rectangles. Which yes is true. This is going to be an x sub n, but I'm going to use instead an I. There's a reason why it gets later. But we're still adding n delta x's. But yeah, rather than that, I'm going to add, so we're adding I delta x's because that subscript matches that. So we're going to call this f of x sub I. Why I'm using I here will make sense in just a moment. All right, so that's the idea. Okay? We're splitting this area into a whole bunch of rectangles, and we're going to add the area of all of the rectangles. So here's what the formula looks like, and then we'll do some examples. So some notation stuff. The symbol looks kind of like that. It's kind of like an S, but not exactly. This is the integral sign. And then we put at the bottom and the top what our starting and ending values are. So this would be read the integral from A to B. That's how that whole chunk would be read. And then we put our function. So we'd say of f of x, okay, dx. That lets us know we're going down to the x value, and our starting and ending values are x values. If we put dy here, it would be that other example that I showed you, where your starting and ending your starting and ending values, your a and b, are y values. So the dx, this dx, and this must go together. You can't write an integral without a dx if you're finding the area under a curve. You can't write an integral without a dy if you're finding the area beside a curve. Just an integral sign by itself begs the question, am I finding the area to the x-axis? Am I finding the area to the y-axis? I don't know. You have to tell me dx or dy. We're only dealing with dx again, but you have to have those together. All right, so here's the formula. Equals the limit as n approaches infinity, so the number of rectangles is going to be an infinite number of rectangles, or approaching infinity, of the sum from I equals 1 to n. In other words, we're going to evaluate the first height of the rectangle plus, to find the area, plus the second height, the height of the second rectangle to find its area, plus the height of the third rectangle to find its area. Okay, so the limit here is saying we're dealing with an infinite number of rectangles. The sum here is for adding the areas of the rectangles. Well, what's the area of a rectangle? It's width. What do we say the width of these rectangles is? Delta x times the height. What's the height? F of x sub I for whichever x value we're dealing with. Okay, so notice from I equals 1. So I equals 1 means evaluate the function with the first x value plugged in times the width of that rectangle plus evaluate the height, find the height using the second, because now I is 2, the second x value times the width plus, because the sum, now I equals 3, etc. And there are two key important things here. Actually, I meant to add of down here, of f of x dx. Sorry about that. So back to here. Delta x, we can say is, well, what are we doing here? Let me scroll up a little bit. We have a width. The total width is b minus a. Right? If you did b minus a, you have the total width that we're dealing with, and then we're splitting it into n rectangles. So our delta x is going to be b minus a over n. And then what is x sub I? X sub I is, well, scrolling back up again, what was our first x? Our x sub 1 was a plus 1 delta x. Our x sub 2 was a plus 2 delta x. So our x sub I we're going to define as a plus I delta x, where you'll actually plug in what delta x equals. And so what we'll do is we'll find what delta x is, then we'll find what x sub I is, then we will plug those into our formula. Then we will find what the sum of the i's is, or are, because you'll have multiple usually. And then we'll evaluate the limit to find what the area is. So we're using a wide variety of things. We're using limits, we're using sigma notation. This a plus I delta x is an extension of arithmetic series. So we have all that stuff going on. So if I kind of put the steps here, first, we want to find delta x. Next, we want to find x sub I. Next, we want to plug delta x into formula and plug x sub I into function in formula. Next, evaluate sigma of the i's, and then evaluate the limit of the n's. Okay? So let's do an example, and yeah, the example will hopefully help a lot. So let's evaluate the limit from 0 to 6 of x squared dx. Okay, so in other words, we want to find the area under this parabola going from an x value of 0 to an x value of 6, and the area from the parabola down to the x-axis. So here's roughly what we're looking at. So the parabola, goes like that, right? So we're going out to 6 here, and we're finding that area like that. Okay? All right. So step 1. Well, let's write our formula. So the limit from 0 to 6 of x squared dx equals the integral from 0 to 6 of x squared dx equals the limit as n approaches infinity of the sum from I equals 1 to n of x sub I. Oops, I put the width first. I think that makes a little bit more sense. Of delta x times, now what's my function? X squared. So I can go ahead and write it as, no, instead of f of x sub I, I'm just going to go ahead and plug it into my function. So what is this? An x sub I squared. Okay, so let's find delta x. Delta x is b minus a over n. So this is 6 minus 0 over n, which is 6 over n. I'm going to hang on to that. So if we were splitting this into 10 rectangles, the width of each rectangle would be 6/10. We are splitting this into an infinite number of rectangles. So the width of each rectangle is 6 over approaching infinity. And then we need our x sub I, we set as a plus I delta x. So that's 0 plus I 6 over n, which we can just write as I 6 over n. Now you could write it as 6i over n. I like to leave the I in front. I'll show you why in just a little bit. Okay, so now we have what we need for plugging in here. So I'm going to say equals. Now you have to keep writing the limit as long as there are n's, and you have to keep writing the sigma notation as long as there are i's, and I'll show you when those go away. But you're going to rewrite limit as n approaches infinity of the sum from I equals 1 to n. You're going to rewrite that a bunch of times. So what's delta x? Delta x is 6 over n. And then what is x sub I? What am I plugging into my function? I 6 over n squared. So I 6 over n squared. Okay, well, let's simplify. So this is the limit as n approaches infinity of the sum from I equals 1 to n of, well, let's see, I have this 6 over n still, but when I square this, I get I squared times what? 36 over n squared. Okay? So this equals the limit as n approaches infinity of the sum from I equals 1 to n of, and if I guess I have this I squared times 36 times 6 is 216. 216 over n cubed. Okay. Now, here is where we get to an important thing. So what's going on here? What's going on here is this sum is we're saying plug 1 in for I. So it's going to be 1 squared times 216 over n cubed plus 2 squared times 216 over n cubed plus 3 squared times 216 over n cubed, etc. Okay? So this part, the sum of I squared, sum from I equals 1 to n of I squared, well, that's 1 squared plus 2 squared plus 3 squared plus ... And we actually have a formula from that, or for that, that this kind of goes back to the infinite sequences and series, or just or in this case, finite. We're pretending like it's finite. We're pretending that it stops at n, even though n is approaching infinity. That's what the limit is for. And what we end up getting is that the sum here equals, I'm going to scoot this over just a little bit to give myself a teeny bit more room. Perfect. The sum equals n times n plus 1 times 2n plus 1 over 6. Likewise, and I guess if I scooch this down a little bit just to kind of keep them in order, if I put the sum of I, so the sum from I equals 1 to n of I, well, that's 1 plus 2 plus 3 plus dot, dot, dot. I should have put a plus there. Plus n. That is the same thing as n times n plus 1 over 2. And if we did the same thing for I cubed, sum I equals 1 to n of I cubed is 1 cubed plus 2 cubed plus 3 cubed plus dot, dot, dot plus n cubed. That is equal to n squared times n plus 1 squared over 4. Now, I will say this. These first two you need to memorize for the test. There are also formulas for n to the fourth, n to the fifth, etc., 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 but just these first two. Because what these allow us to do is they allow us to do this. Remember how I said that as long as there's an I in your formula, you need to keep writing the sigma notation. Well, what is the sum of I squared? It's this formula here. So what we can do is we can write the limit as n approaches infinity of, now we're no longer going to write the sum of I squared, we're going to plug in what the sum of I squared equals. And the sum of I squared equals n times n plus 1 times 2n plus 1 over 6. So this became this. And we still have our times 216 over n cubed. Okay, now let's simplify a little bit. This is the limit as n approaches infinity of, now what does this multiply to be out? What does this multiply out to be? This multiplies out to be 2n cubed plus 3n squared plus n over 6, and we still have this times 216 over n cubed. Okay, well that equals the limit as n approaches infinity of, now if we multiply all this by 216, we would get 432 n cubed plus 648 n squared plus 216 over 6n cubed. Now you might recall from evaluating limits, if you have a polynomial on top and a polynomial on bottom, and what we have is the highest power on top matches the highest power on bottom, then the n cubes end up canceling, and this whole term goes to 0, this whole term goes to 0, and what you're left with is this whole limit equals 432 sixths. The leading coefficients are what stays when the highest power is the same on top and bottom. And 432 over 6 is exactly 72. So that is the area under the curve. It's a bit of work, I know, but this is the nuts and bolts of what's going on when we're finding the area under a curve using calculus. So this one introduced the overall method to you. It introduced how to and when to get rid of the i's and plug in what the formula for the sum of I, in this case, the sum of I squared. It also introduced the idea of evaluating the limit as well as just, the overall process. I'd like to do one more example that throws a couple other new things at you. For example, what do you do if your starting value is not 0? And then what do you do if there's a constant that is part of your function? So one more example. One more example. So let's evaluate. I was going to do. I think I had made up my own. Yeah. Let me double check what that was. It was the integral from 1, from 1 to 3. The integral from 1 to 3 of x squared minus 3x plus 4 dx. All right, here we go. So that is equal to the limit as n approaches infinity of the sum from I equals 1 to n of, and let's just go ahead and find what our nuts and bolts are. Our delta x is b minus a over n, so that's 2 over n. And our x sub I is a, so that's 1, plus I, 2 over n. Okay, a plus I delta x, so 1 plus I, 2 over n. So now we can plug in the sum of the width, delta x. I'm just going to go write this first. Delta x, f of x sub I. So that's the limit as n approaches infinity of the sum from I equals 1 to n of, what's delta x? I'm going to use brackets for these big chunks. 2 over n. What's f of x sub I? It's going to be using my original function here, x squared minus 3x plus 4. Wherever there's an x, I'm going to plug this 1 plus I 2 over n. So it's going to be a 1 plus I 2 over n squared minus 3 times 1 plus I 2 over n plus 4. Okay, let's start to do some simplifying. Equals the limit as n approaches infinity of the sum from I equals 1 to n of, I'm going to leave this 2 over n out front for a while. And let's see what I get here. Well, when I square this chunk, I get 1 times 1, so that's 1, plus 1 times I2 over n plus another 1 times I2 over n. So an I2 over n plus another I2 over n is I4 over n. And then plus, now I square this last term, so that gives me an I squared 4 over n squared. Okay? Minus 3 minus I 6 over n. And I have this plus 4 hanging out still. Okay, let's simplify that. So this gives us equals the limit as n approaches infinity of the sum from I equals 1 to n of this 2 over n times, all right, I'm going to put my I squared term first just because that feels like the highest power thing to me. So an I squared 4 over n squared. Okay, good. Then how many over n's do I have, or how many I terms do I have? I have I 4 over n minus I 6 over n. So that's going to give me a minus I 2 over n. If it's easier for you to view it as we have 4i over n minus 6i over n. Hopefully you can see how that would become a minus 2i over n. All right, that's the math that we're dealing with here. Okay, and then how about my constants? I have 1 minus 3 plus 4, so that's the same thing as 5 minus 3, so that gives us a plus 2. Okay, now, at this point, I can use my sum of I squared. Oops, sorry, I accidentally bumped my screen. I dropped my stylus first, and then I was grabbing it and accidentally bumped the bottom of the screen. Okay, so with this sum of 2 over n, if a term doesn't have any I in it, it is not affected by the sigma, because the sigma only affects the i's. So this you can view as, yeah, it's unaffected by the sigma. So I'm just going to leave that out front still. So we have the limit as n approaches infinity. Now at this point, I'm going to plug in what the sum of I squared is and what the sum of I is. So I'm no longer going to write sigma. I'm just going to write my 2 over n times, now what's the sum of I squared? Well, that's n times n plus 1 times 2n plus 1 over 6. And I still have this 4 over n squared minus what's the sum of I? The sum of I is n times n plus 1 over 2, and I have this times 2 over n. Now, this plus 2, here's the thing. This plus 2, what's going on is we have sum of, so each time we plug in an I, we have a 2 that gets added. So in other words, we have the sum of 2 over n times 1 squared, 4 over n squared, minus 1 times 2 over n plus 2, plus 2 over n times 2 squared, 4 over n squared minus 2 times 2 over n plus 2, plus n over, or 2 over n, 3 squared, 4 over n squared minus 3, etc., plus 2. Each time the I value ticks up 1, we add 2. I value goes up 1, we add 2. I value goes up 1, we add 2. So when all is said and done, we have added 2, a total of however many times we've added I. Well, how many times are we adding I? We're adding I n times. So we've added 2 n times, which means this when the sigma goes away, this plus 2 becomes a plus 2n, because n times we have added that 2 to our equation. That's an important step to catch. Okay. Now we are ready to evaluate the limit once we do a little bit of simplifying. So this is the limit as n approaches infinity. If you do it right, each of your chunks, you'll have, in this case, an n cubed over an n cubed. For this chunk, you'll have an n squared over an n squared, and this chunk, you'll have an n over n. So let's see what we get. The limit, I'm going to leave this 2 over n out maybe one more time and get all of this simplified out. So this becomes, this first part here becomes so n times n plus 1 times 4, we end up getting an 8n cubed plus, what is it usually? N cubed, 2n cubed, right? Yeah, plus, so we have plus 3, so plus 12 n squared plus 4n over 6n squared, okay, good, minus 2n squared plus 2n over 2n. I guess for that matter, you can do a little bit of simplifying even to begin with if you wanted to. If you wanted to, for example, you could say, well, this n cancels with that, and this n cancels with that kind of a thing. That might save you a little bit of work. But I already started doing it this way, so that's okay. So that was, let me erase that. And that, because I'm not doing this. Okay. So that was that chunk, and then plus this 2n. All right, now let's multiply this 2 over n into there. We get the limit as n approaches infinity of, so everything on top gets multiplied by 2, everything on bottom gets multiplied by n. So this gives me a 16n cubed plus 24n squared plus 8n over 6n cubed minus 4n squared plus 4n over 2n squared plus 4n over n. Now we can evaluate these limits. And again, we're able to look at just the leading terms. So if we look at just the leading terms, I'm evaluating the limit, so I'm no longer going to write limit, as I also no longer write any n's. And so my leading terms here become 16 over 6 minus 4 halves plus 4. And when I see what that is, we get 16 sixths. That's what, 8 thirds. So that's 8 thirds minus 2 plus 4. That's the same thing as